Welcome, dear listener. I'm so glad you could join me on this journey of discovery. Wherever you may be in the world right now, whether it's morning, noon, or night, I invite you to settle in, get comfortable, and let my words paint a vivid picture in your mind's eye. If you enjoy immersive stories that blend science and history, weaving a rich tapestry of human ingenuity and natural wonder, then you're in the right place. I'd be honoured if you subscribe to hear more relaxing tales like this. And please, share in the comments where on this marvellous planet you're tuning in from at this very moment. Picture this: a deserted beach stretching as far as the eye can see. Pristine white sand gleams under a luminous full moon, hanging so low and large it seems almost close enough to touch. The inky ocean sparkles with the moon's silvery reflection, undulating gently, as if the sea itself is breathing in and out to some primal rhythm. With each thrumming wave that caresses the shore, the soothing sound washes over you, inviting your mind and body to relax into the timeless cadence of the tides. A light salt-tinged breeze dances over your skin as you marvel at the glowing celestial disk above, the conductor of this mesmerizing symphony of surf and sand. This spellbinding scene, the moon presiding over its aquatic kingdom, has played out unceasingly since Earth's oceans first formed billions of years ago. Long before the first humans walked the world, the moon was there, its gravitational embrace raising and lowering the seas like a cosmic puppeteer, gently tugging on invisible strings. From our earliest ancestors huddled on ancient shores, to sailors navigating by the stars, to modern marine scientists plying the waters, all have gazed up at the moon and felt that sense of wonder, that instinctive pull, even if they didn't fully understand the forces at work. Over the centuries, we've slowly unravelled the secrets of how the moon and tides intertwine in an eternal dance. The greatest minds in history have grappled with this mystery, from Babylonian astronomers to Galileo and Newton, striving to decipher the celestial code that moves entire oceans. And so, dear listener, let us embark on a voyage of discovery, a journey that will take us from ancient shorelines to the frontiers of space. Together we'll explore how the moon came to be master of the tides and how, even today, its influence ripples through every facet of life on our blue planet. As the sound of the waves recedes into the background and my voice carries you deeper into the story, I invite you to let go of the day's cares and slip into a realm where science and storytelling meld into one. Allow yourself to drift on this voyage where past, present and future converge, a place outside of time where the moon reigns eternal. Our story begins over 2,000 years ago on the sun-baked riverbanks of ancient Babylon, a thriving metropolis in what is now Iraq. Here, around 450 BC, a dedicated group of priest astronomers held vigil each night in their towering ziggurat temples, meticulously tracking the motions of the stars, planets and moon. With little more than their naked eyes and keen powers of observation, these proto-scientists, the Chaldeans as they were known, noticed a curious pattern. The waters of the Euphrates River, which flowed wide and muddy through the heart of the city, would rise and fall in sync with the phases of the moon. The highest tides always surged during the full and new moons, while the weakest tides ebbed at the quarters when the moon appeared exactly half illuminated. Month after month, year after year, this cyclical celestial aquatic correspondence held true, too precise to be mere coincidence. The Chaldeans dutifully recorded these tidal patterns on clay tablets, covered in arcane cuneiform script, perhaps the first scientific field notes in history. They had stumbled upon concrete evidence that the moon, earth and ocean were somehow inextricably linked. Though they lacked the physics to fully explain this cryptic connection, the Babylonians had taken the first monumental step in unmasking the moon as the lord of the tides. A riddle that would confound and captivate great minds for centuries to come was now written in the stars and flowing water. One can imagine the sense of awe those ancient astronomers must have felt as they unravelled this cosmological mystery. Gazing up at the moon's lambent face from atop their lofty ziggurats, did they ponder what otherworldly force enabled that luminous disk to move entire oceans from afar? In a time when most believed the heavens were the realm of capricious gods and omens, the Chaldeans dared to seek order and rhythm in the skies. With each meticulous notation of the tide's ebb and flow, they were laying the foundation for a revolutionary idea, that the universe might follow predictable laws which mortals could divine. Little could those Babylonian stargazers have imagined that they were pulling on a thread of knowledge that would one day unspool into a tapestry of celestial mechanics, stretching from their crude clay tablets to the moon itself. They were pioneering a paradigm of patient observation and pattern-seeking that would come to define the scientific method. Nor could they have conceived of how their tidal records, inscribed with reed styluses under the flickering light of oil lamps, would be the first tentative notes in a grand symphony of discovery, a quest to understand the moon's sway over the seas that would span millennia. So let us pause and savour this moment at the dawn of tidal science. In our mind's eye, we can see the first links of a chain of knowledge starting to form, a chain that will stretch unbroken from these Babylonian sages to Galileo, Newton and beyond. As we drift deeper into our story, carried by the moon's ancient rhythms, we'll meet other audacious minds who dared to decode the secrets of the tides. Each will add their voice to the chorus, a symphony of discovery scored in the universal language of mathematics and the poetry of the celestial dance. But for now, let the sound of the ancient Euphrates' flowing waters transport you back across the ages to a moonlit night in old Babylon. Imagine standing atop the great ziggurat, the night wind in your hair, as you join those first astronomers in their faithful vigil. Together you track the moon's stately procession across the star-flecked firmament, marvelling as the river rises in obeisance far below. And for a fleeting moment, the present fades away, and you're caught up in the same primal wonder that has transfixed moonwatchers since time immemorial. As we slip deeper into this entrancing lunar reverie, let your breath fall into rhythm with the ancient tides, your mind adrift on the ebb and flow of the Chaldean's cosmic vision. Breathe in the moon's soothing glow and breathe out the day's cares, in and out, until all that remains is the timeless swell of sea and story. Tethered by threads of starlight and luminous memory, our journey has only just begun. The moon and tides have many more secrets to reveal as we voyage onward through the ages in our quest to unravel the mysteries of their eternal embrace. More than a century after the Babylonians first gleaned the moontide connection, another luminary was drawn into the lunar spell. It was around 330 BC, and the Greek explorer Pytheas of Massalia set out on an epic voyage that would transform him into the Magellan of the ancient world. A contemporary of Alexander the Great, Pytheas was not a conqueror of lands but a pioneer of knowledge. He was driven by an insatiable curiosity about the natural world and a thirst to push beyond the boundaries of the known. In an era when most believed the world ended at the Pillars of Hercules, now known as the Strait of Gibraltar, Pytheas dared to venture through this fabled portal and into the mist-shrouded seas beyond. Braving the untamed Atlantic in his tiny Greek galley, he embarked on an odyssey that would take him further than any Mediterranean mariner before him. With each nautical mile, Pytheas was sailing off the edge of the map, both literally and figuratively. He left behind the familiar coastlines and reassuring landmarks of home, guided only by the sun, stars, and an unwavering inner compass. Day after day, week after week, he pressed northward, carving a bold wake through the heaving swells. The warm blue waters of the Mediterranean gave way to the slate-grey tempest of the Atlantic. The balmy breezes of Greece faded, replaced by the biting gales of the untamed northern reaches. Pytheas and his crew were venturing into a world beyond their wildest imaginings, a world where nature played by different rules. Strange tides surged and ebbed with uncanny power, far beyond anything they'd ever witnessed in their sheltered home seas. Alien constellations wheeled overhead, the reliable celestial beacons of the Mediterranean sky lost beyond the horizon. Yet amidst all this strangeness and adversity, Pytheas's agile mind remained fixed on the task at hand, to observe, to measure, to understand. With each landfall on unknown shores, he meticulously recorded the local customs, climate and geography, compiling a trove of knowledge that would be treasured for centuries. But perhaps his most significant discovery came as he probed ever deeper into the uncharted waters, eventually reaching the frigid coasts of what is now Britain, and even beyond to the fog-bound Orkney and Shetland Islands. Here, at the very edge of the known world, Pytheas witnessed an extraordinary phenomenon that would forever change our understanding of the moon's power over the seas. The intrepid Greek noticed that the ocean tides in these far-flung northern reaches rose and fell with astonishing height and regularity, far more pronounced than the modest tides of the Mediterranean. As he watched the sea surge and withdraw by dozens of feet in a matter of hours, an idea began to take shape in his mind. With a flash of insight, Pythias recognized that the tides were somehow inextricably linked to the moon's phases, just as the Babylonians had proposed centuries earlier. The highest tides always coincided with the full and new moons, while the weakest tides aligned with the lunar quarters. It was as if the moon was a great magnet, invisibly pulling the oceans toward it as it traversed the sky. This was a revelation of cosmic proportions. For the first time, a man had empirically confirmed the moon's sway over the tides, not just in a single location, but across vast swathes of ocean. Pythias had found concrete evidence that the moon's influence extended far beyond the realm of poets and mystics. It was a tangible force that moved entire seas. In that moment of clarity on the wild shores of ancient Britain, Pythias had taken a giant leap forward in unlocking the secrets of the tides. He had built upon the Babylonians' legacy and laid the foundation for centuries of scientific inquiry to come. One can only imagine the sense of wonder and humility Pythias must have felt as he stood on those primordial beaches, watching the moon's celestial dance play out in the surging surf. Did he feel a kindred connection to those long-ago Babylonians who had first glimpsed this truth? Did he marvel at the vast web of natural forces that connected the heavens and earth in ways he was only beginning to fathom? As we picture Pythias, windswept and wide-eyed on the edge of the world, let us savour this pivotal moment in the story of tidal science. With each crashing wave and lunar phase, the ancient Greek was bearing witness to a profound truth, that the moon, earth, and oceans were bound together in an intricate cosmic dance, a dance that would continue to captivate and confound the greatest minds for millennia to come. So let the sound of the surging tides carry you back across the ages to that lonely shore where Pythias once stood. Feel the salt spray on your face and the cool sand beneath your feet as you join him in silent vigil, marvelling at the moon's ethereal glow and the raw power of the seas it commands. In this moment outside of time, you are a part of Pythias's grand adventure, a link in the unbroken chain of discovery that stretches from the Babylonians to the present day. And as we drift deeper into this timeless tableau, the modern world fades away, and all that remains is the moon, the tides, and the irresistible pull of curiosity that drives us ever onward in our quest to understand the cosmos. Breathe in the briny air and breathe out the day's cares, in and out, until your mind is as clear and calm as a moon-drenched sea. For our journey has only just begun, and there are many more secrets waiting to be unveiled in the eternal dance of the moon and tides. More than 1,500 years after Pythias's groundbreaking voyage, another great mind was drawn into the mystery of the moon and tides. It was the early 1600s, and a brilliant Italian scientist named Galileo Galilei was about to revolutionize our understanding of the cosmos. Galileo was a man ahead of his time, a visionary who dared to question the long-held beliefs of his era. In an age when most still adhered to the ancient Aristotelian notion of a perfect, unchanging universe, Galileo was a beacon of empirical inquiry and rational thought. With little more than a homemade telescope and an insatiable curiosity, Galileo unlocked secrets of the cosmos that had eluded humanity for millennia. Night after night, he would train his primitive instrument on the heavens, meticulously recording his observations in a cramped, candle-lit study. What he saw through that tiny lens would forever change our conception of the universe. Galileo discovered mountains and craters on the moon, disproving the long-held belief in its perfect, unblemished surface. He spotted 4 moons orbiting Jupiter, a miniature solar system that dealt a blow to the geocentric dogma of the day. But perhaps most relevant to our story of the tides, Galileo's telescopic observations provided tantalizing hints of the moon's gravitational influence on Earth. As he watched our celestial companion wheel through its phases, Galileo noted how the lunar surface was pockmarked with countless craters and basins, a far cry from the flawless sphere he'd been taught to expect. These imperfections set Galileo's mind racing. If the moon was not a perfect heavenly orb, Might it be more akin to the terrestrial worlds he knew? And if so, could it exert a physical influence on our planet, just as the Earth's gravity held the Moon in its orbit? Galileo never directly studied the tides, but his observations of the Moon's rough Earth-like surface were a crucial stepping stone in understanding its gravitational sway. By daring to question the perfection of the heavens, he had paved the way for a new conception of the cosmos, one in which celestial bodies were not remote and untouchable, but dynamic entities that interacted with each other across vast gulfs of space. As we picture Galileo hunched over his telescope, peering at the Moon's cratered face with rapt fascination, let us marvel at the power of curiosity to unlock the secrets of the universe. With each sketch and notation, the Italian polymath was chipping away at centuries of superstition and dogma, laying bare the true nature of the cosmos, one observation at a time. In that cramped moonlit study, a revolution was taking shape, a revolution of the mind that would eventually transform our understanding of the tides and our place in the grand tapestry of space and time. Galileo may not have grasped the full implications of his lunar discoveries, but he had sown the seeds of a paradigm shift that would soon bear fruit in the work of one of history's greatest scientific minds. So let the sound of Galileo's quill scratching on parchment transport you back to that pivotal moment in tidal history. Feel the cool night air wafting through the window and the rough wood of the telescope beneath your hands as you join him in his moonlit vigil, marvelling at the craters and mountains that no human eye had ever seen before. In this timeless tableau, you are a witness to the birth of a new era in science, a silent partner in Galileo's grand quest to unveil the hidden workings of the cosmos. And as we slip deeper into this luminous reverie, the present fades away, and all that remains is the Moon, the tides, and the irresistible allure of discovery that has driven humanity's greatest minds to reach for the stars. Breathe in the cool, crisp air of Galileo's study, and breathe out the day's cares, in and out, until your mind is as clear and sharp as the view through his telescope. For our journey, transitioning from the poetic musings on the Moon's eternal tidal influence, we find ourselves in the world of ancient Greek astronomy, where philosophers and proto-scientists first began to ponder the mechanisms underlying the ocean's rhythmic rise and fall. Around 384 BC, Aristotle, the famed philosopher and polymath, turned his keen mind to the tides. Like the Babylonians before him, Aristotle noted the correlation between the lunar phases and the height of the tides. He reasoned that the Moon must exert some force on the seas, but the exact nature of this force eluded him. In his treatise, Meteorology, Aristotle proposed that the Moon's motion caused winds, which in turn drove the tides. It was a prescient guess, hinting at the interconnectedness of celestial and terrestrial phenomena, but it would be centuries before the true nature of the Moon's tidal influence was unveiled. Aristotle's student Pytheas, the intrepid Carthaginian explorer we met earlier, added crucial observational evidence to the growing understanding of lunar tidal dynamics. During his daring voyage to the British Isles around 330 BC, Pytheas meticulously recorded the height and timing of the tides at various points along the coast. He noted that the tides peaked consistently at the time of the full and new moons, and were weakest during the quarter moons. Pytheas's findings strongly suggested a causal link between the Moon's phases and the tides, a key piece of the puzzle that would ultimately lead to Newton's gravitational synthesis centuries later. The scene shifts to Alexandria, Egypt, around 150 AD, where we find Ptolemy, one of the greatest astronomers of antiquity, hard at work in the famed Library of Alexandria. Building on the Babylonian and Greek observations of the moontide connection, Ptolemy sought to develop a predictive model of tidal patterns. In his seminal work Tetrabiblos, Ptolemy outlined a complex system of epicycles and deferents to describe the motions of the heavenly bodies, including the Moon. While his geocentric model placed Earth at the centre of the cosmos, a notion that would hold sway for centuries until overturned by Copernicus and Galileo, Ptolemy's mathematical approach to astronomy laid the groundwork for the more sophisticated tidal theories to come. Ptolemy recognized that the height of the tides varied not only with the lunar phases, but also with the Moon's position relative to the equator. He noted that tides were generally higher when the moon was near the equinoxes and lower near the solstices. This observation hinted at the importance of the moon's declination, or angular distance from the celestial equator in modulating tidal forces. Though Ptolemy's model could not fully account for all tidal variations, it represented a significant advance in the quantitative study of the moon's effect on Earth's oceans. As the sun sets over the Alexandria harbour, casting long shadows from the Great Pharos lighthouse, we imagine Ptolemy gazing out at the sea, watching the tides ebb and flow, pondering the cosmic forces at work. The Aegean waves whisper ancient secrets, carrying the knowledge of tides and lunar motions to distant shores and future generations. From Ptolemy's Egypt, we leap forward in time to medieval Europe, where the study of the tides began to take on new urgency as maritime trade and exploration flourished. In the 13th century, we find the English monk and scholar John of Sacrobosco, also known as Johannes de Sacrobosco, penning his influential treatise De Sphera Mundi, or On the Sphere of the World. In this work, Sacrobosco summarized the prevailing astronomical knowledge of his day, drawing heavily on Ptolemy and earlier Arabic scholars. Sacrobosco's De Sphera included a discussion of the tides, which he attributed to the combined influence of the moon and sun. He noted that the tides were highest when the moon was full or new, and lowest at the quarter moons, confirming the ancient observations. Sacrobosco also recognized that the tides varied in height and timing depending on location, with some coastal areas experiencing greater tidal ranges than others. This spatial variability hinted at the complexity of tidal dynamics, with local factors like bathymetry and coastline shape interacting with global celestial forces. De Sphera became a standard astronomy textbook in medieval universities, shaping the education of generations of scholars and laying the foundation for the scientific revolution to come. Its clear, concise explanations and diagrams of the lunar phases and tidal cycles made these complex phenomena accessible to a wider audience, sparking curiosity about the natural world and humanity's place in the cosmos. As we imagine Sacrobosco scratching away by candlelight in a cloistered scriptorium, the distant sound of waves echoes through the stone hallways, a reminder of the endless dance of moon and tide beyond the monastery walls. The flickering flame illuminates intricate diagrams of the celestial spheres, the moon's pale visage exerting its silent pull on the parchment pages and the oceans alike. The scene dissolves, and we find ourselves in the bustling port city of Venice in the early 16th century. The Venetian Republic is at the height of its power, with a vast network of trade routes crisscrossing the Mediterranean and beyond. Ships laden with spices, silk, and other precious cargo navigate the labyrinthine canals and lagoons, their movements dictated by the rhythms of the tides. It is here that we meet Italian physician and astronomer Girolamo Fracastoro, a contemporary of Copernicus and a key figure in the early scientific revolution. Fracastoro is best known for his pioneering work on contagious diseases, but he also made significant contributions to the study of the tides. In 1538, he published his treatise Homocentrica, in which he proposed a novel explanation for the tides based on the Earth's rotation and the attraction of the moon and sun. Fracastoro's theory was a departure from the prevailing Aristotelian and Ptolemaic models, which relied on complex systems of celestial spheres and epicycles to explain the motion of the heavens. Instead, Fracastoro suggested that the Earth rotated on its axis daily, causing the apparent rising and setting of the stars and planets. He reasoned that this rotation, combined with the gravitational pull of the moon and sun, caused the oceans to slosh back and forth, producing the tides. While Fracastoro's model was ultimately incorrect in its details, it represented a crucial step towards a more physically grounded understanding of the tides. His idea of the Earth's rotation, though controversial at the time, would be vindicated by Copernicus and Galileo in the decades to come, and his notion of the moon and sun's attractive force on the oceans hinted at the concept of universal gravitation, which Newton would later develop into a powerful quantitative theory. As the Venetian sunset paints the lagoon in shades of gold and crimson, we picture Fracastoro deep in thought, poring over astronomical charts and tidal observations in his study overlooking the Grand Canal. The distant cries of gulls and the creaking of ship masts carry on the evening breeze, a reminder of the ceaseless ebb and flow of the tides, the moon's invisible hand guiding the fortunes of sailors and nations alike. From the opulence of Renaissance Venice, we turn our gaze to the windswept shores of Brittany in the mid-17th century. The French astronomer and priest Jean Picard, a contemporary of Newton and Huygens, has taken up the challenge of unravelling the secrets of the tides. Armed with a keen eye, a telescope, and a passion for precision, Picard sets out to make the most accurate tidal measurements yet attempted. In 1679, Picard establishes a tidal observatory at the harbour of Brest, carefully recording the height and timing of the tides over several years. His meticulous observations reveal subtle patterns and variations that had escaped earlier researchers. Picard notes that the tides not only follow the lunar phases, but also exhibit a fortnightly cycle, with the highest tides occurring near the new and full moons and the lowest near the quarter moons. This spring-neap cycle is a key signature of the moon's gravitational influence, as Newton would later show. Picard also discovers that the tidal range, or difference between high and low tide, varies over the course of the year, with the highest tides occurring near the equinoxes in March and September. This annual variation, known as the equinoctial tide, is caused by the alignment of the Sun and Moon's gravitational pulls during these times, an effect that would later be quantified by Laplace and others. Picard's precise measurements and keen insights set the stage for Newton's groundbreaking work on the tides in the 1680s. By providing a wealth of empirical data and identifying key patterns, Picard helped pave the way for the development of a truly quantitative and predictive theory of the tides. As we stand with Picard on the ramparts of the Brest Observatory, the Atlantic breeze tugging at our hair and the cry of gulls echoing in the distance, we marvel at the dedication and ingenuity of this unsung hero of tidal science. The lighthouse beam sweeps across the darkened sea, illuminating the restless waves, a silent tribute to the enduring mystery and beauty of the moon-driven tides. From the lonely vigil of Jean Picard, we return to England and the intellectual ferment of the late 17th century. In Cambridge, a young Isaac Newton is grappling with the implications of his newfound theory of universal gravitation. Having developed the mathematical framework to describe the force of attraction between any two objects in the universe, Newton turns his attention to the long-standing puzzle of the tides. In his masterwork, the Principia Mathematica, published in 1687, Newton dedicates an entire section to the analysis of tidal phenomena. Drawing on the observations of Picard, Halley and others, as well as his own mathematical insights, Newton constructs a comprehensive theory of the tides based on the gravitational interaction of the Earth, Moon and Sun. Newton realizes that the key to understanding the tides lies in the differential gravitational force exerted by the Moon, and to a lesser extent the Sun across the Earth's surface. He reasons that the side of the Earth facing the Moon experiences a slightly stronger gravitational pull than the centre of the Earth, while the opposite side experiences a slightly weaker pull. This imbalance results in a net force that stretches the Earth's oceans outward on both sides, creating two tidal bulges that follow the Moon's apparent motion around the Earth. Newton's theory elegantly explains the twice-daily rise and fall of the tides, as well as the spring-neap cycle and other variations noted by earlier observers. He shows that the height of the tides depends on the relative positions of the Moon and Sun, with the highest tides occurring when their gravitational pulls align at new and full moons, and the lowest when they partially cancel each other out at quarter moons. Newton's tidal theory is a triumph of mathematical physics, demonstrating the power of his universal law of gravitation to explain seemingly disparate phenomena with a single, unified framework. It marks a turning point in the history of tidal science, transforming a collection of empirical observations into a coherent quantitative theory with predictive power. As we imagine Newton, quill in hand, scratching out equations by candlelight in his study at Trinity College, the distant tolling of bells and the murmur of the River Cam drift through the leaded windows. The Moon, once a mysterious force, is now bound by the laws of physics, its secrets laid bare by the power of Newton's mind. And yet, as the silver orb rises over the spires of Cambridge, casting its spell on the river's ripples, we sense that the Moon's magic and mystery endure, forever intertwined with the rhythms of the tides and the dreams of those who gaze upon its face. From the intellectual heights of Newton's Cambridge, we descend the bustling streets of 18th century London, where a new generation of tidal researchers is grappling with the challenges of turning theory into practice. Among them is the eminent astronomer and mathematician John Machine, best known for his work on lunar theory and his role in promoting Newton's ideas. In 1738, Machine presents a groundbreaking paper to the Royal Society, in which he applies Newton's tidal equations to the problem of predicting the times and heights of high and low tides at specific locations around the British coast. Machine's work represents a crucial step forward in the practical application of tidal theory, laying the foundation for the development of accurate tide tables and navigation aids. Machine begins by refining Newton's equations to account for the effects of local topography, wind and atmospheric pressure on tidal heights. He collects a wealth of tidal data from harbours and coastal communities around Britain, using it to calibrate his mathematical models and improve their predictive power. One of Machine's key insights is the importance of harmonic analysis in understanding tidal patterns. He recognises that the complex rise and fall of the tides can be broken down into a series of simpler, periodic components, each driven by a specific combination of lunar and solar forces. By identifying and quantifying these harmonic constituents, Machine is able to create a more accurate and flexible model of tidal behaviour that can be adapted to different locations and conditions. Machine's work lays the groundwork for the development of the first reliable tide tables, which become an essential tool for maritime navigation and coastal planning in the 18th and 19th centuries. His methods are refined and extended by subsequent generations of tidal researchers, including Pierre-Simon Laplace and William Thomson, Lord Kelvin, who use increasingly sophisticated mathematical techniques to unravel the complexities of ocean tides. As we stroll along the banks of the Thames, the sound of ships' bells and the cries of dock workers echoing across the water, we reflect on the enduring legacy of John Machine and his fellow tidal pioneers. Their tireless efforts to map the moon's influence on the Earth's oceans have made the once mysterious tides a little less daunting, a little more predictable. And yet, as the river's currents swirl and eddy beneath the London Bridge, we are reminded that the tides, like the moon itself, will always retain an element of wildness and wonder, an untamable force that shapes our world in ways both seen and unseen. As the 19th century dawns, the study of the tides enters a new era of precision and sophistication, driven by advances in mathematics, physics, and technology. At the forefront of this tidal renaissance is the brilliant French mathematician and astronomer Pierre-Simon Laplace, whose groundbreaking work on celestial mechanics and probability theory revolutionizes our understanding of the cosmos. In his monumental 5-volume treatise Mécanique Céleste, Celestial Mechanics, published between 1799 and 1825, Laplace devotes considerable attention to the problem of the tides. Building on the foundations laid by Newton, Bernoulli and others, Laplace develops a comprehensive mathematical theory of tidal dynamics that accounts for the complex interplay of lunar, solar and terrestrial forces. Laplace's tidal equations, known as the Laplace tidal equations, are a set of partial differential equations that describe the motion of the oceans under the influence of gravitational and rotational forces. They take into account factors such as the Earth's rotation, the inclination of the lunar and solar orbits, and the effects of friction and local bathymetry on tidal flows. One of Laplace's key insights is the importance of long-period tidal constituents in shaping ocean tides. He shows that in addition to the familiar diurnal and semi-diurnal tides, there are also slower, multi-day, and even multi-year tidal cycles driven by the changing positions of the Moon and Sun relative to the Earth's equator and perihelion. These long-period tides, while small in amplitude, can have significant effects on global ocean circulation and climate patterns over time. Laplace's tidal theory also sheds light on the phenomenon of tidal resonance, whereby certain coastal areas experience amplified tidal ranges due to the shape and depth of the local seafloor. He shows that in shallow enclosed basins like the Bay of Fundy or the Bristol Channel, the natural period of oscillation of the water can match the period of the tidal forcing, leading to greatly enhanced tidal heights and currents. Laplace's work on the tides is a testament to the power of mathematical analysis in unravelling the mysteries of the natural world. His equations provide a unified framework for understanding and predicting tidal behaviour across a wide range of scales, from the local to the global, the short term to the long term. They lay the foundation for modern tidal science and continue to inform research on ocean dynamics, coastal processes and climate change to this day. As we imagine Laplace, ensconced in his study in the heart of Paris, surrounded by stacks of papers and astronomical instruments, the distant chiming of church bells and the clatter of horse-drawn carriages filter through the shuttered windows. The candle on his desk flickers as he works late into the night, his quill scratching out page after page of equations, the moon's phases and the tide's ebb and flow reduced to a symphony of symbols and numbers. And yet, as the first light of dawn seeps into the room, casting a pale glow on Laplace's tired face, we sense that his quest to understand the tides is far from over, that the moon's mysteries will continue to beckon and inspire for generations to come. From the rarefied heights of Laplace's Paris, we turn our attention to the rugged shores of 19th century Scotland, where a young William Thompson. As we drift off to sleep, our minds wander back to the ancient city of Alexandria, Egypt in the year 150 AD. In the famed Library of Alexandria, the great astronomer and mathematician Ptolemy pores over star charts and tide records. Building on centuries of Babylonian and Greek knowledge, Ptolemy pieces together a pioneering model of lunar motion and its effects on Earth's tides. In his treatise Almagest, Ptolemy describes the complex epicycles and deferents that he believes govern the moon's orbit. While his geocentric model will later be overturned, Ptolemy's meticulous observations of the moon's phases and the tides establish a critical link. He notes the synchronicity of spring tides during new and full moons when the sun, earth, and moon align, and neap tides during quarter moons when they form a right angle. Ptolemy's insights will remain the most sophisticated understanding of lunar theory and tides for more than 1,000 years. But as the centuries unfold, a new age of exploration dawns. In the 15th century, Prince Henry the Navigator of Portugal establishes a legendary navigation school at Sagres. Under his visionary patronage, a cadre of daring mariners and brilliant cartographers push the boundaries of the known world. As Portuguese caravels ply uncharted waters, they carefully log the strange tidal patterns they encounter. Captains like Vasco da Gama and Ferdinand Magellan marvel at the dramatic 40-foot tidal ranges along the African coast and the diurnal tides of the South China Sea that rise and fall just once a day rather than twice. Their detailed tide logs become treasured resources, studied by astronomers and natural philosophers across Europe. One such scholar is Galileo Galilei, who in 1616 is invited to deliver a series of lectures on the tides to the Florentine court. Galileo seizes the opportunity to champion his Copernican view of the solar system, with the sun, not Earth, at the centre. In a bold claim, Galileo argues that the tides are caused not by the moon, but by the sloshing of Earth's oceans as our planet wobbles through space. It's a daring theory, but one that fails to convince his contemporaries, who point to the undeniable correlation between the lunar phases and tidal cycles. Galileo's flawed tidal theory becomes a lifelong source of frustration and even embarrassment for the great astronomer. Yet his public lectures spark a fervent debate about the tides across 17th century Europe, fueling the scientific revolution. Meanwhile, on the other side of the world, Chinese and Japanese scholars are making their own lunar breakthroughs. In the year 1639, the Chinese astronomer Xuefeng Suo compiles a comprehensive tidal atlas, mapping the complex tides along the country's vast coastline. Zhe's work is a marvel of detail and accuracy, reflecting the Chinese tradition of meticulous celestial observation dating back millennia. In Japan, the samurai-turned-astronomer Shibukawa Shunkai makes a startling discovery. After years of observing ocean tides in the night sky, Shibukawa notices that the tides seem to follow the lunar calendar, not the solar calendar. In his 1749 treatise, Shibukawa proposes that the moon phase is the true driver of the tides, an insight that parallels the work of Newton and Laplace in Europe. As the Age of Enlightenment unfolds, the tide of scientific understanding surges forward. The moon's secrets begin to yield under the probing minds of the era's great thinkers. Yet even as the mysteries of the tides slowly ebb, new questions arise. For the moon, our ancient companion, still holds many secrets. The lapping of waves and the distant keening of gulls bring us back to the present, to the salt-tanged breeze and moon-silvered shore. The eternal rhythm of the tides echoes the cadence of history, an ebb and flow of discovery and wonder. And as we slip softly into slumber, the moon keeps her silent vigil, an impassive sentinel guarding the vast, undulating oceans of our water world. In our dreams, we walk in the footsteps of ancient astronomers and sail with legendary navigators, all bound by a common quest to unravel the celestial clockwork above. The moon's phases paint our sleeping imaginings, her ghostly luminescence a lantern guiding us through the corridors of time. We dream of Aristotle on the shores of Lesbos, pondering the ebb and flood of the Aegean Sea, of Seleucus of Seleucia, who in 150 BC boldly proclaimed the moon as the cause of the ocean's tides. In our mind's eye, we see the glittering courts of Chang'an and Baghdad, where astronomers and astrologers alike debated the moon's sway over terrestrial affairs. The visions shift, and suddenly we're aboard the storm-tossed caravel of Christopher Columbus, marvelling at the strange tides of the New World. We feel the salt spray and hear the creak of timbers as Columbus jots in his log that the tides are not like those of the Mediterranean. It is a small observation, but one that will open a floodgate of inquiry. Time winds onward in our reverie, and we find ourselves peering over the shoulder of Edmund Halley, of comet fame, as he puzzles over the intricacies of tidal flows in the English Channel. In his 1684 tidal map, the first of its kind, Halley traces the progressive motion of tidal crests, marvelling at their speed and regularity. It is a glimpse of the unseen lines of force that bind sea to sky. We catch dreamlike snippets of other luminaries, Giovanni Cassini measuring the parallax of the moon, Pierre Gassendi proposing a mechanical model of the tides, William Ewell coining the term scientist to describe this new breed of inquisitive minds. Each figure is a thread in the tapestry of discovery, a reminder of the ceaseless human drive to know and understand. As the first blush of dawn paints the horizon, and the moon fades into a pale ghost, our dreams dissolve like sea foam. But the wonder lingers, a silent echo of the tides within our veins. For just as the moon's gravity tugs at the vast oceans, so too does it tug at our imaginations, drawing us ever onwards in the quest for knowledge. The waves whisper a final lullaby as we surface from the depths of sleep, our minds awash with the moon's tidal pull, the eternal ebb and flow of discovery, mirroring the rise and fall of the sea. And though the journey is long and the destination uncharted, we take comfort in the knowledge that the moon will light our way, a celestial beacon guiding us through the cosmic ocean of wonder. The story of how the moon controls Earth's tides is also a tale of scientific perseverance, ingenuity, and occasional serendipity. Progress was rarely straightforward. More often it came in fits and starts, with insights hard-won through diligent observation, rigorous calculation, and occasional flashes of brilliance. One such flash lit up the mind of German astronomer Johannes Kepler in the early 17th century. Though best known for his laws of planetary motion, Kepler was also intrigued by the ebb and flow of ocean tides. Building on the ideas of ancient scholars and contemporary observations, Kepler proposed that some kind of force from the moon must be responsible for the tide's regular cycles. In a stroke of insight, Kepler suggested that the moon might be exerting an attraction on the Earth's oceans, drawing the waters outward into a tidal bulge. He even speculated that a similar force from the sun could account for smaller tidal variations. Though he lacked the mathematical tools to prove it, Kepler had intuited the fundamental mechanism behind the tides. It would be left to later generations of scientists to quantify and refine Kepler's initial hunch. In the 1640s, Italian astronomer Giovanni Battista Riccioli and his assistant Francesco Maria Grimaldi undertook detailed measurements of the tidal range in the Adriatic Sea. Painstakingly tracking the rise and fall of the ocean surface, they showed conclusively that the tides ebbed and flowed in time with the moon's orbit around the Earth. Riccioli and Grimaldi's work caught the attention of England's royal court, where a young Isaac Newton was beginning to turn his singular intellect to the mysteries of motion and force. Already pondering the hidden dynamics that kept the moon circling the Earth and the Earth orbiting the sun, Newton began to wonder, could the same invisible force be tugging on the terrestrial oceans? Delving into the data gathered by Riccioli, Grimaldi and others, Newton slowly pieced together a unifying theory of gravitation that could explain the tides, the trajectories of planets, and the fall of an apple in an English orchard. In his masterwork, the Principia Mathematica, published in 1687, Newton laid out his universal law of gravitation, describing how every mass in the universe attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Applying this law to the Earth-Moon system, Newton painted a picture of the Moon's gravitational field reaching across space, tugging on the Earth's oceans and drawing them outward into two bulges, one on the side facing the Moon and another on the opposite side. As the Earth rotated beneath these bulges, Newton explained, the seas would seem to rise and fall, producing the twice-daily cycle of high and low tides. But Newton knew his work was not yet complete. The real ocean tides were far more complex than his simplified model suggested. They varied in height and timing from place to place, and didn't always line up exactly with the Moon's position in the sky. To fully explain the tides, Newton realized he would need to account for complicating factors like the Earth's rotation, the tilt of its axis, the influence of the Sun's gravity, and the irregular contours of coastlines and seafloors. Though Newton made a start at refining his tidal theory, the sheer complexity of the problem defied even his peerless gifts. Passing the torch to the next generation, Newton expressed his hope that others might take up the challenge and carry this to a higher degree of perfection. Rising to Newton's call was the brilliant French mathematician Pierre-Simon Laplace. Born more than 40 years after Newton's death, Laplace inherited a world transformed by Newton's insights, but he also recognized how far tidal science still had to go. Leveraging his mastery of calculus and mechanics, Laplace set out to extend and generalize Newton's tidal equations. In a series of groundbreaking papers published in the late 18th century, Laplace laid out what came to be known as the dynamic theory of tides. His equations accounted for variations in the Moon's orbital path, the Sun's perturbing influence, and the effects of Earth's rotation and equatorial bulge. Laplace's refined models could predict tidal patterns with unprecedented accuracy for any point on the globe. Laplace's tidal equations were a tour de force of mathematical physics, but they were devilishly difficult to solve by hand. The calculations required to forecast tides involved endless iterations and mind-numbing arithmetic. Doing them by hand could take months or even years, limiting their practical use. It would take another century and a new generation of computing technology before Laplace's tidal equations could be fully implemented. In the 1860s and 70s, William Thomson, later known as Lord Kelvin, developed a series of mechanical tide-predicting machines capable of rapidly churning through the complex calculations. These analog computers, with their whirring gears and spinning pulleys, were hailed as marvels of ingenuity, cutting the time to calculate tides from months to mere hours. Thomson's tide predictors found eager customers among port authorities and shipping magnates the world over. For the first time, sailors and dock managers could plan ahead with detailed knowledge of when tides would rise and fall. The machine's clicking rhythms played counterpoint to the timeless cadence of the ocean surf, a harmony of natural cycles and human invention. But even as Thomson's devices were transforming tidal forecasting into a practical science, new astronomical observations were revealing hidden complexities in the Moon's sway over the seas. In the late 19th century, Irish astronomer George Darwin, son of Charles, undertook a series of meticulous measurements of the Moon's orbit and rotation. To his surprise, Darwin found small but persistent discrepancies between the Moon's observed motion and that predicted by Newton and Laplace's gravitational theories. Darwin realized these anomalies hinted at some additional, as yet unknown, influence on the Moon's orbit. Might the Earth's oceans themselves be exerting a subtle tug on the Moon? Following this lead, Darwin constructed an elaborate mathematical model of the gravitational interplay between the Earth, Moon, and the shifting tides. His calculations revealed a fascinating picture. Not only was the Moon's gravity raising tides on the Earth, the tides were pulling back on the Moon. Each day, as the Earth rotated beneath its two tidal bulges, those watery masses would get slightly ahead of the Moon's orbital position, dragging on the satellite and slowing its motion. At the same time, the Moon's persistent gravitational tug acted as a brake on the Earth's rotation, lengthening the day by about 1.8 milliseconds per century. This slow, synchronized dance, Darwin showed, had been going on for eons, with the Earth's spin gradually winding down as the Moon spiraled away at roughly 3.8 centimeters per year. Projecting this trend backward in time, Darwin proposed a remarkable scenario. Some 4.5 billion years ago, the Moon must have orbited much closer to the Earth, whipping around our planet every few hours. The proximity would have raised enormous tides on the Earth's surface, miles high by some estimates, that helped shape our planet's early evolution, possibly even contributing to the origin of life. Darwin's work brought the study of the tides full circle. What had begun as an effort to understand the ocean's daily rhythms now offered a sweeping view of Earth's history and destiny. The tides were more than a curiosity. They were a key that could unlock the secrets of the past and point the way to the future. As the 20th century dawned, tide science continued to advance in leaps and bounds. With the advent of electronic computers in the 1940s and 50s, tidal predictions grew ever more precise and detailed. Faster calculation speeds enabled scientists to model the tides in 3 dimensions, accounting for underwater topography and coastline geometry with unprecedented fidelity. At the same time, new generations of tide gauges and oceanographic instruments were deployed to gather ever more sophisticated data on sea level heights, current patterns, and deep ocean conditions. Tide stations that had once been isolated outposts now formed nodes in a growing global network, feeding a constant stream of measurements to scientists and forecasters around the world. One of those scientists was Walter Munk, a titan of 20th century oceanography. Born in Austria in 1917, Munk fled the country after the Nazi annexation, eventually making his way to the United States and the Scripps Institution of Oceanography in La Jolla, California. There, he threw himself into the study of the tides, seeing in their regular rhythms a key to understanding the ocean's role in weather, climate, and Earth's rotation. Over a career spanning more than 7 decades, Munk made groundbreaking contributions to tidal science. He pioneered the use of underwater acoustics to measure ocean temperatures and currents, revealing the 3-dimensional structure of tidal flows. He quantified the dissipation of tidal energy through seafloor friction and turbulence, showing how the tides act as a brake on the Earth's rotation. And he elucidated the complex gravitational interplay of the Earth, Moon, and Sun, deriving equations that could predict tides with uncanny accuracy. But perhaps Munk's most enduring legacy was his infectious passion for the science of the sea. He saw the tides not merely as a physical phenomenon to be studied, but as a grand symphony to be savoured. "I have come to love the tides almost as much as I love my very best friends," he once wrote. "To this day I take delight in watching the tides come and go, much as a child might watch the waves break on the shore." Munk's sense of wonder has inspired generations of tidal researchers who have followed in his footsteps. Today, equipped with satellite altimeters, supercomputer models, and a deepening understanding of the interconnections of sea and sky, these scientists are pushing the boundaries of what we know about the tides and their role in the Earth system. From ancient Babylon to the space age, the quest to comprehend the tides has been a mirror for our growing understanding of the world and our place in it. Each advance has revealed new depths to the Moon's influence on our planet, shaping not just the rhythms of the ocean, but the very course of life on Earth. And yet, for all our scientific sophistication, the tides still retain a hint of mystery and romance. Their ceaseless rhythms, ordained by celestial clockwork, remind us of forces beyond our control, of cycles that have been turning since long before we arrived and will continue long after we're gone. Perhaps that is why so many of us feel drawn to the ocean's edge, to watch the tide's eternal ebb and flow. In their constancy, we sense a comforting continuity, a connection to something larger than ourselves. And in their endless variety, we see reflected the enduring human quest for knowledge and understanding. So the next time you find yourself on a beach at night, watching the moonlit waves roll in, pause and ponder the celestial dance playing out before you. The rise and fall of the tides may seem simple, even predictable, but they are a reminder of the intricate web of forces that bind our world together, and of the indomitable human drive to unravel those hidden connections. In the end, the story of the tides is the story of our unending fascination with the world around us, a love affair with the simple mysteries and complex wonders that make our planet such an endlessly enchanting place. It is a story written in the stars and etched in the sands, whispered by the wind and roared by the surf. And it is a story that, like the tides themselves, will continue as long as the moon still circles overhead, and curious minds still turn to the horizon, forever seeking to understand the vast, beautiful and changeable sea. The tides may rise and fall, but the moon's celestial sway remains unbroken, a gravitational waltz as old as time itself. As we continue our journey through the annals of history, we find ourselves transported to the windswept shores of 19th century England, where a remarkable woman was about to make her mark on the world of tidal science. Her name was Janet Taylor, born in 1804 to a humble family in the Yorkshire countryside. From a young age, Janet displayed an uncanny aptitude for mathematics and a keen fascination with the sea. Despite the societal constraints placed upon women of her era, Janet's passion for knowledge could not be contained. At the age of 22, Janet moved to London, determined to carve her own path in the male-dominated world of science. She began working as a teacher, earning a meagre wage while spending her nights poring over astronomical texts and nautical charts. It was during these long hours of study that Janet first encountered the works of Pierre-Simon Laplace, the French mathematician who had refined Newton's tidal equations a century earlier. Inspired by Laplace's groundbreaking work, Janet set out to make her own contributions to the field of tidal prediction. In 1833, she established a navigational academy in London, where she taught sailors the intricacies of celestial navigation and tidal calculation. Her school quickly gained a reputation for excellence, attracting students from across the British Empire. But Janet's true legacy would be her tireless efforts to improve the accuracy of tidal predictions. In an era before computers or satellite data, predicting the tides was an arduous task, requiring countless hours of manual calculation. Janet recognized the immense value that reliable tide tables could provide to mariners and coastal communities alike. With an almost superhuman dedication, Janet set about compiling tide tables for ports around the world. She spent years meticulously analyzing tidal data, refining her calculations to account for the myriad factors that influence the rise and fall of the seas. From the gravitational pull of the moon and sun to the effects of local geography and weather patterns, Janet left no stone unturned in her quest for precision. Her hard work paid off in 1847 when she published her magnum opus, Janet Taylor's Lunar Tables for Calculating Distances. This groundbreaking volume contained a wealth of tidal data and predictions, allowing sailors to navigate with unprecedented accuracy and safety. The book quickly became an indispensable tool for mariners worldwide, cementing Janet's reputation as one of the foremost tidal experts of her time. But Janet's contributions extended far beyond the realm of navigation. Her work laid the foundation for modern tidal science, paving the way for future generations of researchers and oceanographers. She demonstrated that even in an age of limited technology and societal barriers, one woman's passion and perseverance could illuminate the mysteries of the seas. As we reflect on Janet Taylor's extraordinary life and legacy, we are reminded of the power of curiosity and the enduring allure of the tides. Just as the moon's gravitational embrace shapes the rhythms of our oceans, so too can a single person's dedication shape the course of human knowledge. Today we stand on the shoulders of giants like Janet Taylor, Laplace and Newton, marvelling at the intricacies of the cosmic dance between Earth and its celestial companions. With each passing tide, we are reminded of the countless minds that have sought to unravel these ancient rhythms, driven by an insatiable hunger to understand the world around us. And so, as we drift off to sleep, lulled by the gentle crashing of waves upon the shore, we can take comfort in the knowledge that the tides will continue their eternal ebb and flow, guided by the moon's unwavering presence. It is a dance that has endured for eons and will continue long after we are gone, a testament to the immutable laws of nature that bind our world together. In the end, the story of the tides is not just a tale of scientific discovery, but a reflection of the human spirit itself. It is a reminder that no matter how vast and complex the universe may seem, there will always be those among us who dare to dream, to explore, and to push the boundaries of what is possible. So let us embrace that spirit of wonder and curiosity, just as Janet Taylor did so many years ago. Let us gaze up at the moon with renewed appreciation for its cosmic influence, secure in the knowledge that its gravitational waltz will endure long after we have faded into the annals of history. For in the end, the tides may be fleeting, but the legacy of those who have sought to understand them is as enduring as the moon itself. It is a legacy that echoes through the ages, whispered in the crash of every wave and etched in the hearts of all who have ever been captivated by the sea's eternal mysteries. And so, we bid good night to the moon and the tides, secure in the knowledge that they will continue their ancient dance long after we have drifted off to sleep. It is a dance that has shaped our world since time immemorial, and one that will endure for generations to come, a testament to the unwavering rhythm of the cosmos itself. As we sail through time, the early 19th century brings us to the shores of Brest, France, where an unassuming customs officer named Laplace is about to make waves in the world of tidal science. Alexis Bouvard, appointed director of the Paris Observatory in 1811, tasked Laplace with improving the accuracy of tide predictions. Little did Bouvard know, he had just set in motion a revolutionary leap forward in our understanding of the moon's gravitational grip on Earth's oceans. Laplace, a brilliant mathematician and astronomer, set about the challenge with gusto. He knew that predicting tides wasn't just an academic pursuit. The livelihoods and lives of countless sailors, fishermen, and coastal dwellers depended on it. Building on the groundbreaking work of Newton a century earlier, Laplace refined and extended the tidal equations, taking into account the complex interplay of Earth's rotation, the inclination of the moon's orbit, and even the more subtle gravitational influences of the sun. Night after night, Laplace burned the midnight oil, his quill scratching out page after page of intricate calculations. He was determined to demystify the rhythms of the tides once and for all. In 1799 he presented his magnum opus on the subject, the Traité de Mécanique Céleste, or Treatise on Celestial Mechanics. Within its pages, Laplace laid out a comprehensive mathematical framework for understanding and predicting tidal patterns with unprecedented accuracy. Laplace's equations were a revelation, but they were also fiendishly complex. Calculating tides for any given location and time required laboriously working through a series of complicated formulae, a task that could take even the most skilled mathematician hours or days. But Laplace's work had laid the foundation, and in the coming decades others would build upon it to make tidal prediction more practical and accessible. One such individual was William Thomson, a brilliant young Scottish physicist who would later become known as Lord Kelvin. In the 1860s, Thomson became fascinated by the problem of tidal prediction and set about designing a machine that could do the job automatically. His invention, the tide predicting machine, was a marvel of ingenuity, a brass wood and wire contraption that could mechanically solve Laplace's equations and churn out tidal predictions for any port in the world. Thomson's machine was a game changer. No longer would tidal calculations require painstaking manual labour. Now they could be done quickly, accurately, and on demand. Shipping companies, naval bases, and port authorities around the globe clamoured for access to Thomson's device and the tidal predictions it produced. In an era where maritime trade was the lifeblood of the global economy, reliable tide tables were worth their weight in gold. But Thomson's interest in the moon's tidal influence didn't stop there. He was also fascinated by the question of how the moon's gravitational pull affected Earth's rotation over long periods of time. Thomson realised that the tidal bulges the moon raised on Earth acted as a sort of brake, slowly but surely slowing down the planet's rotation. At the same time, Earth's tidal pull on the moon was gradually pushing it into a higher orbit, increasing the distance between the two bodies. It was a stunning insight, a cosmic dance of gravity and inertia playing out over millions of years. Thomson calculated that Earth's day was lengthening by about 2 milliseconds every century, due to this tidal braking effect. Correspondingly, the moon was spiralling away from us at a rate of about 3.8 centimetres per year. Imperceptible on human timescales, but over eons these tiny changes added up to a profound reshaping of our world. As the 19th century drew to a close, our understanding of the moon's tidal influence had advanced by leaps and bounds thanks to the work of pioneers like Laplace and Thomson. But the quest to fully decipher the mysteries of the tides was far from over. In the coming decades, a new generation of scientists and inventors would take up the challenge, armed with ever more sophisticated mathematical tools and an insatiable curiosity about the workings of our watery world. From the tide gauges and tidal stations that began to spring up along coastlines worldwide, to the advent of modern satellite oceanography, the 20th century would see tidal science transformed from an art into a precise data-driven discipline. But as we'll see, even with all the advances of modern technology, the moon still held plenty of surprises in store for those seeking to unravel its secrets. As night falls and the moon rises once again over our tranquil beach, its silvery light painting shimmering paths across the waves, we're reminded of the timeless power of this celestial body to shape and reshape our world in ways both subtle and profound. The tides may seem like a simple, everyday occurrence, but behind their rhythmic ebb and flow lies a fascinating story of scientific discovery and human ingenuity that continues to unfold this day. The tidal forces that gently rock our oceans back and forth are but one manifestation of the intricate gravitational dance that binds the Earth and Moon together. As we've seen, this cosmic pas de deux has been slowly but surely reshaping our planet over billions of years, lengthening our days, altering the Moon's orbit, and even influencing the evolution of life in the tidal zones along our coasts. But the story doesn't end there. As we continue to study the Moon and its tidal effects with ever greater precision, we're uncovering new insights into everything from the internal structure of our planetary companion to the role of tides in global climate patterns. The Topex Poseidon and Jason satellite missions of the late 20th and early 21st centuries, for instance, have given us an unprecedented global view of ocean surface topography, allowing scientists to map tidal patterns worldwide with centimetre-level accuracy. These satellite data, combined with advanced computer modelling techniques, are helping researchers to better predict not only day-to-day tidal fluctuations, but also longer-term changes in sea level and coastal erosion patterns. In an era of accelerating climate change and rising oceans, this knowledge is becoming increasingly vital for coastal communities around the world. But even as we harness the power of modern technology to study the Moon's tidal influence in ever greater detail, there's still something awe-inspiring and humbling about the simple act of standing on a beach and watching the tide roll in and out. It's a reminder of the vast cosmic forces that shape our world in ways we're only just beginning to fully comprehend. And so, as we drift off to sleep to the sound of the waves gently lapping at the shore, we can take comfort in the knowledge that the Moon will continue to work its ancient magic, tugging and sculpting the oceans with its invisible gravitational hands, just as it has for billions of years. It's a celestial lullaby that has soothed and inspired countless generations of humans, and will continue to do so for countless more to come. As the poet Rumi once wrote, "The Moon is a loyal companion. It never leaves. It's always there, watching steadfast, knowing us in our light and dark moments, changing forever just as we do." The Moon and the Tides, a cosmic love story for the ages, playing out in the eternal dance of gravity and inertia, water and rock, light and shadow. It's a reminder of the beauty, mystery, and interconnectedness of our world, and of the enduring human quest to understand and find our place within it. And so, let us give thanks to the Moon, our faithful friend and celestial guardian, as we drift off into dreams of crashing waves, shimmering tides, and the endless dance of the heavens above. Good night, and may the Moon watch over you always. As the Moon's gentle glow bathes the tranquil beach, we're reminded of the enduring fascination this celestial body has held for humanity across the ages. From ancient astronomers to modern scientists, the Moon has been a constant source of wonder, mystery, and scientific inquiry. One such inquiring mind belonged to George Darwin, son of the legendary naturalist Charles Darwin. In the late 19th century, George turned his keen intellect towards the heavens, seeking to unravel the secrets of the Moon's origin and its inextricable link to Earth's oceans. Born in 1845, George Darwin grew up immersed in the world of science, often accompanying his father on expeditions and absorbing his meticulous approach to natural observation. But while Charles focused his genius on the evolution of life on Earth, George was drawn to the stars above. As a young mathematician at Cambridge University in the 1870s, George began to ponder the complex gravitational dance between Earth and its lunar partner. Building upon the groundbreaking work of Newton and Laplace, he delved deeper into the mathematical intricacies of tidal forces. In a series of pioneering papers, George proposed a radical new theory, that the Moon was born from Earth itself, wrenched from our planet's surface by the immense tidal forces generated by a rapidly spinning young Earth. This cataclysmic event, he suggested, hurled a mass of molten rock into orbit, which eventually cooled and coalesced into the moon we see today. George's fission theory of lunar formation was a bold and imaginative leap, painting a dramatic picture of Earth's early history. He envisioned a planet spinning so fast that a day lasted a mere 2 to 4 hours, its surface a roiling sea of magma. The gravitational forces at play would have been immense, enough to overcome Earth's own gravity and launch a portion of its mass into space. While George's fission theory has since been eclipsed by other models of lunar formation, such as the giant impact hypothesis, his work was a catalyst for new ways of thinking about Earth-Moon dynamics. His mathematical insights laid the foundation for modern tidal theory, and his creative approach to cosmic origins inspired generations of planetary scientists. George also recognized the profound influence of tidal friction on Earth's rotation. Just as William Thompson had described the moon's braking effect, George calculated that Earth's day would have been much shorter in the distant past, gradually lengthening over eons due to the moon's gravitational drag. He even pondered the ultimate fate of the Earth-Moon system, suggesting that tidal forces might eventually cause the moon to recede so far that it would take 47 days to orbit Earth, locked in synchronous rotation like a cosmic ballet. It was a stunning vision of a far future Earth, forever changed by the moon's relentless gravitational embrace. Throughout his career, George Darwin's passion for unravelling the moon's mysteries never waned. He once wrote, "The moon is the only body in the heavens whose motions can be accurately predicted. She is the only witness we have of the early history of our Earth." His words capture the sense of awe and curiosity that has driven lunar science for centuries. As we lie here on this moonlit beach, listening to the soothing rhythm of the tides, we can't help but marvel at the incredible story of how we came to understand the moon's power over our oceans. From the Babylonians' keen observations to George Darwin's provocative theories, the human mind has been unravelling this celestial riddle step by step, century by century. And yet, for all our scientific progress, the moon has lost none of its ancient allure. It remains a captivating presence in our night sky, a silver guardian forever sculpting our oceans and igniting our imaginations. As we drift off to sleep, the sound of waves gently lapping the shore, we dream of giant collisions, spinning proto-Earths, and the endless cosmic dance of Earth and Moon. The tides may ebb and flow, but the moon's mystery endures, inviting us to keep gazing upward in wonder. George Darwin's legacy reminds us that the story of the moon is also the story of Earth, a tale of origins and evolutions entwined. His bold ideas marked a new chapter in our understanding of the Earth-Moon system, a vision of a dynamic, ever-changing cosmos. And while the details of his fission theory have been refined over time, his spirit of scientific curiosity and imagination lives on in the work of today's lunar explorers. As we continue to study the moon with ever more sophisticated tools, from gravity mapping satellites to lunar landers and rovers, we're uncovering new chapters in this eons-old story. We're learning about the moon's interior structure, its seismic shivers, and the icy secrets that may lurk in shadowed craters at its poles. And as we plan for a new era of lunar exploration, with dreams of permanent moon bases and a launching pad for voyages to Mars and beyond, we're reminded that the moon is not just an object of scientific study, but a destination, a frontier to be explored. In the coming decades, humans may once again walk on the moon's surface, following in the footsteps of Neil Armstrong and Buzz Aldrin, leaving new bootprints in the ancient lunar dust. Perhaps, as those future astronauts gaze back at Earth from the moon's airless heights, they'll marvel at the sight of the blue marble they call home, its oceans swirling with tides pulled by the very ground beneath their feet. They'll be witnessing the gravitational embrace that has bound Earth and Moon for billions of years, a celestial pas de deux choreographed by the laws of physics. And as they radio their observations back to Earth, their voices travelling across the vast lunar distance, they'll be adding new verses to the epic poem of Earth and Moon, a story that began long before us and will continue long after we're gone. They'll be the latest in a long line of lunar explorers, from the Babylonians to George Darwin to the Apollo astronauts, all united by a shared sense of wonder at the moon's eternal presence. As we finally drift into sleep's warm embrace, the moon's gentle light filtering through our window, we feel a sense of connection to that great story, a thread that links us to all those who have ever gazed up at the moon and marvelled. The tides may rise and fall, but the moon's gravitational lullaby is always there, a constant reminder of the cosmic dance that has shaped our world and our dreams since time immemorial. In our mind's eye, we see the moon in all its phases, from the thinnest silver crescent to the luminous full moon, each one a chapter in an endless story. We see the tides flowing in and out like the breath of the planet, the pulse of the oceans in sync with the beat of the cosmos. And we see ourselves, tiny figures on a moonlit beach, witnesses to the grand ballet of earth and moon, participants in a story that has no end. As sleep finally claims us, the moon watches over us, a silver sentinel in the night sky, its light a reminder of the wonders that await us in the vast cosmic ocean above. And though we may drift off to realms of dreams, the moon remains, forever pulling at the tides of our world and the tides of our imagination, a celestial companion on the long journey through the night and into the dawn of a new day filled with the promise of new discoveries under its eternal light. The story of the moon and the tides is one that spans millennia, a grand saga of celestial clockwork on a scale almost beyond human comprehension. And yet, as we've seen, humanity's greatest minds have slowly unravelled this mystery piece by painstaking piece. But the moon's influence extends far beyond the oceans. Its gentle gravitational caress shapes life itself. The ebb and flow of the tides, born from that distant lunar pull, have been the metronome of coastal ecosystems since the dawn of a life on Earth. Consider the mangrove forests that hug tropical shorelines. These tangled cathedral forests with their stilt-like roots and verdant canopies are nurseries for countless marine species. Fish, crustaceans and mollusks seek shelter within the submerged roots during high tide, emerging to feed as the waters recede. This pulsing cycle of abundance and retreat is choreographed by the moon's gravitational ballet. Or ponder the armies of horseshoe crabs that storm Atlantic beaches each spring to spawn. These living fossils, virtually unchanged for over 400 million years, time their mass reproductive gatherings with the peak, high tides of the full and new moons. The extreme tides afford protection for their eggs, burying them deep in the sand, safe from predators and desiccation. The moon is both matchmaker and guardian to these ancient arthropods. Even in the frigid polar regions, the moon's tidal influence holds sway. Beneath the thick sea ice, tidal currents continually pump nutrients upward from the depths, nourishing the phytoplankton that bloom along the ice's undersurface. These microscopic algae are the foundation of the polar food web, sustaining krill, fish, and ultimately the whales and seals that embody the mythic megafauna of these icy realms. The moon's unseen hand helps feed the largest creatures on Earth, but the moon's tidal influence doesn't stop at the water's edge. Even creatures of the land and air dance to the lunar rhythms. Many species of coastal birds, like the tiny sanderlings that skitter along the surf, time their foraging with the tides. As the water retreats, these shorebirds probe the exposed sand for mollusks and marine worms, refueling for their epic migrations. The moon is their clock, their tide tables etched in instinct. Some land mammals also sync their lives to the lunar pulse. The moon-guided tides help red fox populations time their nocturnal hunting forays along the coast, as the retreating water exposes a bounty of crabs, fish, and invertebrates. Inland, some prey species, like mice and rabbits, may alter their nighttime activity patterns based on the amount of moonlight, a behaviour shaped by eons of dodging moonlight-aided predators. Even in our forests and fields, the moon's glow tells an ancient story. For the creatures of the sea and shore, the moon is the great conductor, setting the tempo and rhythm of their lives. Its gravitational score, played out in the swelling and retreating tides, has been a driving force of evolution, weaving itself into the genes and behaviours of countless species. This is a reminder that even the most distant astronomical phenomena can have profound impacts on the intricate web of life on Earth. But what of our own species? Certainly modern humans, with our electric lights and 24/7 schedules, have largely broken free of the moon's sway. Or have we? There's a reason we speak of howling at the moon, or blame it for temporary insanity. Even the word lunatic comes from the Latin luna, or moon. While such beliefs may be more folklore than science, they speak to a deep, primal awareness of the moon's power. In truth, the moon's tidal influence has shaped human culture and history in profound ways. For millennia, coastal communities have planned their lives around the tides: when to fish, when to travel, when to gather precious resources exposed by the retreating sea. The moon has been our ancient clock, our celestial calendar, guiding the rhythms of our ancestral lives. Even in the age of satellites and GPS, the moon's tidal pulse still beats at the heart of maritime culture. Ship captains and harbour pilots must intimately know the local ebb and flow, lest they run aground or miss a narrow window of deep water. Surfers and beachgoers check the tide tables as religiously as the weather forecast. The moon's gravitational drumbeat remains the background music of life along the shores. And what of the future? As humanity looks to extend its presence to the stars, the moon remains our first waypoint, our gateway to the cosmos. Its tidal lock, the result of eons of gravitational tug-of-war, means that one side permanently faces Earth, a cosmic front porch awaiting our return. The same tidal forces that shape our oceans have also gifted us a stable platform for astronomical observation and a potential staging ground for missions to Mars and beyond. Perhaps, as we establish lunar bases and observatories, a new generation of moon dwellers will look back on Earth and marvel at the blue and white marbled beauty of the tides in motion. They'll witness the power of the moon's gravitational embrace on a planetary scale, a celestial dance that has been ongoing since the Earth first cooled and the oceans first formed. And so, as we drift off to sleep, let us dream of the moon and its eternal tidal song. May we find comfort in the constancy of its phases, and solace in the ceaseless rhythm of the waves upon the shore. For in a world of change and uncertainty, the moon abides, a silver guardian watching over the blue marble of Earth, its gravitational lullaby a reminder of the deep cosmic connections that bind us all. The tides may rise and fall, the seasons may come and go, but the moon's gentle pull remains a constant, a celestial heartbeat that echoes through the ages. It is a reminder that even in our vast, often inscrutable universe, there is a rhythm and a reason, a pattern and a purpose that transcends our terrestrial concerns. So let us give thanks to the moon, our eternal companion, sculptor of oceans and shaper of life. May its silver light guide us through the tides of change and challenge, and may its gravitational embrace remind us of our place in the grand cosmic dance. As we slip into the realm of dreams, let the sound of the surf be our lunar lullaby, a whispered reminder of the moon's eternal presence and power. For in the ebb and flow of the tides, in the waxing and waning of the lunar phases, we find a mirror of life's own rhythms, the highs and lows, the light and shadow that define our mortal journey. And though we may be but a cosmic blink in the grand sweep of time, we are nonetheless part of this ancient celestial waltz, our lives and fates tied to the moon's eternal cycle. So let us find solace and serenity in its constant presence, a beacon of permanence in an ever-changing world. Good night, dear listener, and may the moon's gentle light guide your dreams and soothe your soul. For in the end, we are all children of the tides, our lives shaped by the unseen pull of the heavens above. And in that cosmic connection, we find a sense of belonging, a reminder that we are part of something greater, a celestial dance that has been ongoing since the dawn of time. So let us embrace the moon's mystery and magic, and let its eternal rhythms be a source of comfort and wonder. For as long as the moon endures, as long as the tides continue their timeless dance, we too shall endure, our stories woven into the grand tapestry of the cosmos. And with that we bid you a peaceful night, secure in the knowledge that the moon watches over us, its silver smile a promise of constancy in an inconstant world. May its gentle light guide you to the shores of sleep, where the sound of the surf echoes the rhythm of the universe itself. Good night, and sweet lunar dreams. As we drift off, our minds lulled by the moon's gentle influence on the tides, we find ourselves transported back in time once more to the year 1609. Galileo Galilei, an Italian astronomer and mathematician, sits hunched over his workbench, carefully grinding and polishing lenses to create one of the world's first telescopes. With each meticulous movement, Galileo inches closer to a discovery that will forever change our understanding of the cosmos and our place within it. As he fits the final lens into place, Galileo lifts the telescope to his eye and points it toward the heavens. What he sees through the lens astounds him. The moon, once thought to be a perfect, unblemished sphere, is revealed to be a world of mountains, of valleys and craters. Galileo's heart races as he sketches the lunar landscape, marvelling at the imperfections that make the moon so beautifully unique. Though Galileo's observations focused on the moon's surface features, his work would lay the foundation for future astronomers to explore the complex relationship between the moon and Earth's oceans. His telescope, a gateway to the stars, opened up a new era of scientific discovery and understanding. As news of Galileo's lunar observations spread throughout Europe, a young Englishman named Isaac Newton began to ponder the implications of these findings. Born in 1643 in Woolsthorpe by Colsterworth, a small village in Lincolnshire, England, Newton was a precocious child with an insatiable curiosity about the natural world. In 1665, as the Great Plague swept through England, Newton retreated to his family's estate in Woolsthorpe. It was during this time of isolation and contemplation that Newton began to formulate his groundbreaking theories on gravity and motion. He wondered, could the same force that caused an apple to fall from a tree also be responsible for keeping the moon in orbit around Earth? Newton's musings would culminate in his magnum opus, Principia Mathematica, published in 1687. In this seminal work, Newton laid out his universal law of gravitation, which stated that every particle in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This elegant equation revealed that the moon's gravitational pull on Earth was the key to understanding the rise and fall of the tides. Newton realized that the moon's gravity caused the oceans to bulge outward on both the side facing the moon and the side opposite it. As Earth rotated beneath these bulges, the tides would rise and fall in a predictable pattern. Newton's tidal theory was a triumph of mathematical genius and creative intuition. By unifying the celestial and terrestrial realms under a single set of physical laws, Newton forever changed our understanding of the universe and our place within it. His work would inspire generations of scientists to explore the intricate dance between Earth, moon, and sea. As we imagine Newton, quill in hand, scratching out the equations that would unlock the secrets of the tides, we can't help but marvel at the power of the human mind to unravel the mysteries of the cosmos. From ancient Babylonian astronomers to Galileo and Newton, the story of our understanding of the moon's influence on Earth's oceans is a testament to the enduring human spirit of curiosity and discovery. With Newton's revelations still echoing in our minds, we find ourselves drifting further into the realm of dreams, the gentle rhythm of the tides, a soothing lullaby. The moon, our constant companion, watches over us as we slumber, its silvery light a reminder of the eternal connection between the heavens and the earth. As the night deepens and the moon traces its ancient path across the sky, we find ourselves transported once more through the annals of history. The year is 1776, and the Age of Enlightenment is in full flourish. In the bustling streets of Paris, a brilliant young mathematician named Pierre-Simon Laplace is about to make a groundbreaking contribution to our understanding of the moon's influence on Earth's oceans. Laplace, born in Beaumont-en-Auge, Normandy, in 1749, displayed an early aptitude for mathematics. By the age of 24, he had already made significant contributions to the field of probability theory and caught the attention of the scientific elite in Paris. It was here, amidst the intellectual ferment of the French capital, that Laplace would turn his prodigious mind to the problem of the tides. Building upon the foundation laid by Newton a century earlier, Laplace set out to refine and extend the mathematical description of tidal forces. He recognized that Newton's theory, while groundbreaking, did not account for the many complexities that influenced the tides, such as Earth's rotation, the inclination of the moon's orbit, and the gravitational pull of the sun. With quill and parchment, Laplace worked tirelessly, developing a set of differential equations that more accurately described the ebb and flow of the tides. His equations took into account the interplay of celestial bodies and the intricacies of fluid dynamics, painting a more comprehensive picture of the tidal forces at work. Laplace's tidal equations were a marvel of mathematical elegance and predictive power. By incorporating the various factors that influence the tides, Laplace was able to create a model that could accurately forecast tidal patterns for any location on Earth at any point in time. This was a revolutionary development for coastal communities and seafarers, who could now anticipate the rise and fall of the tides with unprecedented precision. As we picture Laplace hunched over his desk, his mind lost in a world of mathematical abstractions, we can't help but be amazed by the sheer intellectual firepower he brought to bear on the problem of the tides. His work represents a crucial link in the chain of scientific discovery, connecting the insights of Newton to the modern era of tidal prediction and oceanographic research. Laplace's contributions to our understanding of the tides were not limited to the purely theoretical realm. His equations provided a practical tool for navigators and coastal engineers, allowing them to plan for the safe passage of ships and the construction of harbours and docks. In a sense, Laplace's work helped to tame the unruly power of the tides, making the oceans a little less mysterious and a little more manageable. As we drift deeper into the realm of sleep, the gentle whisper of Laplace's equations still echoing in our minds, we can't help but feel a sense of awe at the incredible ingenuity and perseverance of the scientists who have unravelled the secrets of the tides. From ancient Babylon to the streets of Paris, the story of our understanding of the moon's influence on Earth's oceans is a testament to the enduring human quest for knowledge and understanding. The moon, ever-present and enigmatic, continues its eternal dance with Earth, the tides rising and falling to the rhythm of Laplace's timeless equations. And as we surrender to the embrace of sleep, we can rest assured that the tides will continue their ceaseless ebb and flow, a cosmic waltz set in motion by the delicate balance of celestial forces. From the shoreline we now soar upwards, our mind's eye rising through wisps of clouds, higher and higher, until the spherical curve of the Earth comes into view, a blue marble suspended in inky space, and there, floating serenely in the distance, her watchful gaze forever fixed on our spinning world, is the moon. Constant yet ever-changing, her alabaster face waxing and waning in a celestial rhythm as old as time itself. As we hang here in the silent void, it's almost impossible to believe that this distant luminous companion, 250,000 miles away, could have any tangible influence on our world. And yet, as we've seen, she's forever pulling and tugging on the fabric of our oceans, a relentless gravitational dance that shapes the very shorelines and heartbeat of our planet. To understand this ancient partnership between the moon and tides, we must first rewind the clock some 4.5 billion years to the very birth of the Earth-Moon system. Most scientists believe that in the chaotic early days of the solar system, a Mars-sized object collided with the proto-Earth, a cosmic crack-up of unimaginable violence. From the seething debris kicked up by this impact, our moon coalesced and began her long journey alongside our battered world. In those early days, the moon orbited far closer to Earth, perhaps a mere 15,000 miles away compared to the 240,000 miles of today. So close that she would have loomed enormous in the sky, some 24 times larger than we see now. Imagine the tide such a nearby moon could create. Immense bulges of water ripping around the planet, scouring and shaping the surface in ways difficult to comprehend. A very different world than the one we know today. But even as the moon slowly spiraled away from Earth over hundreds of millions of years, settling into her current orbit, her influence on the oceans remained profound, and it was this ceaseless sculpting that would play a crucial role in the evolution and diversification of life on Earth. For as those ancient tides rose and fell, they carved out ecological niches along primeval shorelines, tide pools, estuaries, and intertidal zones teeming with opportunity for early life to exploit. The rhythmic advance and retreat of the tides created a dance of exposure and inundation, of desiccation and hydration, that would drive the evolution of specialized adaptations in Earth's pioneering organisms. In the sun-dappled shallows of those Archean tide pools, some 3.5 billion years ago, minuscule cyanobacteria learned to photosynthesize, harnessing the sun's energy to split water and liberate oxygen. This tidal zone alchemy would slowly transform Earth's atmosphere, paving the way for the diversity of aerobic life we know today. As the eons unfolded, life's dance with the tides grew more elaborate. Intertidal creatures evolved biological clocks to anticipate the moon's rhythm, their metabolisms and behaviors syncing with the rise and fall of the waves. Fiddler crabs scuttled in perfect time with the tides, their feeding and mating cued by the moon's phases. Grunion fish rode the highest spring tides onto the beach to spawn. Their fertilized eggs then washed back to sea on the next high water. Even land plants found ways to exploit the tidal rhythm. Mangroves, with their tangled roots reaching into brackish shallows, evolved complex filtration systems to cope with the twice-daily influx of salt water brought by the tides. Their fallen leaves carried out to sea became the building blocks of intricate food webs, nourishing everything from tiny invertebrates to the largest whales. And of course there is us, Homo sapiens. We too have been shaped by the moon's tidal influence, perhaps in more ways than we realise. For our ancient ancestors, living in coastal caves or along marshy estuaries, the tides would have been an inescapable presence, dictating the rhythms of sustenance and survival. Tidal patterns would have governed the availability of shellfish, the migrations of fish, even the salinity of drinking water. Over time, an innate awareness of the tides would have been an evolutionary advantage, a key to staying fed and watered. Some anthropologists believe this could have been a driving force in the development of human mathematical thinking and timekeeping, the first stirrings of science sparked by the moon's metronomic dance. As human cultures blossomed, the tides shaped our histories and mythologies. For the ancient Egyptians, the annual flooding of the Nile, which irrigated their crops and renewed the fertility of the soil, was a gift of the moon god Khonsu. They tracked the phases of the moon to predict the coming inundation, a celestial calendar that ordered their agricultural lives. Halfway around the world, the indigenous Yolngu people of northern Australia have rich oral traditions surrounding the tides. In their cosmology, the tides are the heartbeat of the creator snake, each high tide a surge of its life-giving power, each low tide an exhalation. The Yolngu also recognized the connection between the moon's phases and the tides, using this knowledge to plan their coastal foraging and sacred ceremonies. For seafaring cultures the world over, the tides have been both ally and adversary. The ancient Polynesians, peerless navigators of the Pacific, learned to read the tides like a map, using their ebb and flow to trace a path between far-flung islands. Their epic voyages of discovery, guided by the stars and tides, would eventually people islands from Hawaii to New Zealand, a watery realm encompassing nearly a third of the Earth's surface. On the other side of the world, the Vikings of Scandinavia also harnessed the power of the tides. These fearsome mariners timed their coastal raids and trading expeditions to coincide with the highest tides, allowing their shallow draft longships to penetrate deep inland along river estuaries. In this way, the reach of the Vikings was extended by the moon's gravitational hand, a cosmic assist in their reshaping of medieval Europe. The tides played a pivotal role in one of the most famous military invasions in history, the Norman conquest of England in 1066. William, Duke of Normandy, timed his channel crossing to take advantage of the high tides at Pevensey on September 28th. This allowed his fleet of invasion barges to beach high on the shore, avoiding the treacherous mudflats and shallows that could have spelled disaster. Once again, the moon's tidal influence had tipped the balance of history. Fast forward to World War II, and the tides once more took centre stage during the D-Day landings at Normandy. The Allies had to navigate a narrow tidal window, landing at low tide to avoid German underwater defences, but not so low that their landing craft would be stranded far from shore. It was a delicate balancing act requiring meticulous tidal calculations. The moon, it seemed, would decide the fate of nations. As we've journeyed through the ages, we've seen how the moon's tidal influence has shaped our world and histories in profound ways, even as its scientific workings remained cloaked in mystery for millennia. But now, armed with Newton's laws and modern scientific instrumentation, we're finally uncovering the full complexity of Earth's tidal dynamics. We now know that the moon's gravitational pull is just one part of an intricate tidal equation. The sun also plays a vital role, its gravity working in tandem with the moon's to create the highest spring tides and the lowest neap tides. Topography matters too. The shape of coastlines, the depth of ocean basins, the presence of islands and continents all affect how tides propagate around the planet. In some places, like the Bay of Fundy in Canada or the Severn Estuary in England, these factors conspire to create truly colossal tidal ranges. Imagine a 50-foot wall of water surging up a narrow inlet, then draining away again just hours later. These are some of the largest tidal swings on Earth, a testament to the staggering amounts of energy the moon and sun can pump into our oceans. And that energy is not just shaping our shorelines, but the very planet itself. As the moon's gravity drags those immense tidal bulges around the Earth, it creates friction between the ocean waters and the seabed. This tidal friction acts as a gentle brake on the Earth's rotation, imperceptibly lengthening our days by about 2 milliseconds per century, a slow, relentless tick-tock ordained by the cosmos. At the same time, the Earth's rotation attempts to drag the tidal bulges ahead of the moon, creating a gravitational torque that transfers angular momentum to the moon. This nudges the moon into a slightly higher orbit and causes it to speed up a bit in its orbit around the Earth. The end result is that the moon is gradually spiralling away from us at a rate of about 1.5 inches per year, a cosmic retreat measured in slow motion. It's a poetic dance of angular momentum. The Earth spins slowing as the moon pirouettes away, like figure skaters moving in perfect counterbalance. And it's been going on for billions of years, a gravitational pas de deux as old as the Earth-Moon system itself. But even as the moon slowly waltzes into the distance, its tidal influence remains a powerful force on our world. Today, we're harnessing that power in new ways, using the immense energy of the tides to generate clean, renewable electricity. Tidal power stations like the Lorance plant in France or the Sihwa Lake station in South Korea use the predictable ebb and flow of the tides to spin turbines and light up cities, the moon's gravitational pull transformed into megawatts. And as we look to the future, the moon's tidal influence may play an even more crucial role. With rising sea levels due to climate change, understanding and predicting tidal patterns has never been more important. Coastal communities worldwide are grappling with more frequent flooding, eroding shorelines, and saltwater intrusion into freshwater aquifers. The moon, it seems, will have a hand in shaping our environmental future just as it has our past. Yet for all the challenges the tides may bring, there is also a profound beauty and sense of connection in their eternal rhythm. For as long as the moon continues its cosmic dance around our world, the tides will remain a reminder of our place in a vast and interconnected cosmos. A twice-daily whisper from the heavens, echoing across the ages that we are all bound together by forces far grander than ourselves. And so, as we drift off to sleep tonight, let's take a moment to marvel at that pale silver disk hanging low in the sky. Our moon, our celestial companion, the sculptor of our world. Whether we're watching the waves lap at our feet, or simply dreaming of distant shores, we're all forever touched by her tidal embrace, a gravitational lullaby that has cradled life on Earth since time immemorial. The tides may be inconstant, the moon ever-changing, but in their eternal cycle, there is a constancy and comfort that transcends the ages, a reminder that no matter how much our world may shift and change, there are rhythms and patterns that endure, cosmic heartbeats that have pulsed since the dawn of time and will continue long after we're gone. So let the sound of the waves and the soft glow of the moon lull you into a peaceful slumber, secure in the knowledge that you are part of a grand and ancient tapestry, woven by the gravitational threads of the cosmos itself, a beautiful, intricate dance of moon and tide and life, playing out on the shores of our pale blue dot suspended in the void. Sweet dreams under the moon's watchful gaze. May her tidal lullaby carry you gently into the night, a soothing reminder of our place in the grand cosmic ballet. The moon and tides, forever intertwined, a celestial pas de deux without end. Drifting back in time once more, we find ourselves in the bustling port city of Venice, Italy in the year 1595. The famed Galileo Galilei, not yet the iconic astronomer we remember today, is a young professor of mathematics at the University of Padua. He's been tasked with a seemingly mundane problem: how to control the frequent flooding of the Venetian lagoon, which threatened the city's vital maritime trade. Galileo, ever the keen observer, noticed a peculiar pattern in the flooding. It seemed to follow a predictable cycle, with the highest tides occurring every 2 weeks, around the full and new moons. Intrigued, he began meticulously recording the water levels, correlating them with the lunar phases. Night after night, Galileo would sit by the edge of the lagoon, a quill in one hand and a makeshift water level measuring tool in the other. The soft lapping of waves and distant calls of gondoliers formed a soothing backdrop to his studies. He marvelled at how the moon, that distant serene orb, could invisibly orchestrate the rise and fall of these mighty waters. Galileo's tidal observations were among the first to be systematically recorded in the Western world. Though he never fully unravelled the mystery of the moon's gravitational pull, his meticulous data hinted at a profound connection between the celestial and terrestrial realms. These early studies would plant the seed for Galileo's later groundbreaking astronomical discoveries. Just as the moon's phases could predict the tides, so too could the movements of Jupiter's moons mark the passage of time, as he would famously demonstrate in 1610. Galileo's genius was in his ability to discern the hidden patterns that underlie nature's seeming chaos. As we sit with Galileo by the moonlit lagoon, we can almost sense the gears turning in his mind, a mind that would later overturn centuries of dogma and revolutionize our understanding of the cosmos. But for now he's simply a curious young man, captivated by the moon's ethereal glow and the endless dance of the tides. The scene dissolves, and we find ourselves transported to the rugged coast of Brittany, France in the year 1701. A lone figure stands atop a windswept cliff, silhouetted against the twilight sky. He is Edmund Halley, the brilliant English astronomer best known for predicting the return of the comet that bears his name. But Halley's interests spanned far beyond comets. He was fascinated by the Earth's magnetic field, atmospheric physics, and crucially for our story, the ocean tides. Halley had long been intrigued by the moon's role in the tides, building upon the pioneering work of Galileo and Newton. In 1691, Halley had published a seminal paper on the topic, in which he proposed that the tides were caused by the combined gravitational pull of the moon and sun. He even created a simple mechanical model to demonstrate how these celestial forces could create the complex tidal patterns observed around the world. But there was one phenomenon that confounded Halley: the dramatic difference in tidal ranges between various locations. Why did some places, like the Bay of Fundy in Canada, experience enormous 50-foot tides, while others, like the Mediterranean Sea, saw barely a ripple? To unravel this mystery, Halley embarked on an ambitious project to map the tides of the English Channel and the North Atlantic. And so we find him here, on this rugged Breton coastline, armed with a sextant, compass and an early chronometer. Night after night, Halley would meticulously measure the height and timing of the tides, comparing his observations to the lunar cycles. He braved the frigid Atlantic winds, his measurements often made by the light of the very moon he was studying. Slowly a pattern began to emerge. Halley realized that the shape of the coastline and the depth of the ocean floor played a crucial role in amplifying or dampening the tidal range. Shallow, funnel-shaped bays tended to have the highest tides, while deep, open oceans experienced much smaller tidal swings. This insight was revolutionary. For the first time, the seemingly capricious tides could be understood not just as a product of celestial mechanics, but of terrestrial geography as well. Halley's charts of the Atlantic tides, painstakingly drawn by the light of the moon, laid the foundation for modern tidal prediction. As we stand with Halley on that windswept cliff, watching the moonlit waves crash against the rocks, we can sense the excitement of discovery that must have coursed through his veins. In the rhythmic ebb and flow of the tides, he had glimpsed a hidden order, a symphony of the celestial and terrestrial realms. The scene fades, Halley's figure merging into the moonlit mist. We are left with a renewed appreciation for the dedicated astronomers and natural philosophers who slowly unravelled the moon's tidal secrets, one observation at a time. Their patient vigils, often conducted under the moon's watchful gaze, laid the foundation for our modern understanding of the cosmos. As we drift off to sleep, lulled by the timeless lullaby of the tides, we can almost imagine Galileo and Halley standing watch with us, marvelling at the moon's eternal mastery of the oceans. In the silver stillness of the night, their spirits live on, a testament to the enduring power of human curiosity and the celestial wonders that continue to captivate us, even in our dreams. Fading back into consciousness, we find ourselves in the familiar surroundings of the Royal Observatory in Greenwich, England. The year is 1833, and the man hunched over a cluttered desk, surrounded by piles of papers and gleaming brass instruments, is Sir George Biddell Airy, the 7th Astronomer Royal. Airy, a brilliant polymath and meticulous observer, had a particular fascination with the moon and its effect on the Earth's tides. Building upon the work of his predecessors like Halley and Newton, Airy set out to create the most accurate tidal predictions yet attempted. Night after night, Airy would pore over tidal records from ports around the world, painstakingly transcribing the data onto neatly ruled sheets. The soft scratching of his quill and the ticking of the observatory's precision clocks formed a soothing backdrop to his calculations. Airy's breakthrough came in the form of the harmonic analysis of tides. He realized that the complex tidal patterns could be broken down into a series of simple sine waves, each representing the influence of a different astronomical body: the Moon, the Sun, even distant planets like Jupiter and Venus. By combining these harmonic components, Airy could predict the tides for any location with unprecedented accuracy. His methods, refined and automated over the decades that followed, formed the basis of the tidal prediction tables that are still used by mariners and coastal engineers today. But Airy's tidal studies were more than just an exercise in mathematical virtuosity. They spoke to a deeper truth about the interconnectedness of all things, from the cosmic to the oceanic. Just as the moon's gravity could shape the rhythm of the tides, so too could distant planets imperceptibly influence the wobble of the Earth's axis. As we sit with Airy in his cluttered study, watching him work by the flickering light of an oil lamp, we can sense the quiet thrill of discovery that animates his calculations. In the precise dance of the heavenly bodies, he had found a mirror for the elegant equations that flowed from his pen. The scene dissolves, and we find ourselves back on that pristine beach where our journey began. The moon still hangs low over the horizon, its reflection shimmering on the gently undulating waves. But now, as we listen to the rhythmic crash of the surf, we hear it with new ears. In the ebb and flow of the tides, we can sense the echo of ancient Babylonian astronomers, the whispered calculations of Galileo and Halley, the precise predictions of Airy and his successors. The moon's gravitational symphony, once a mystery, now sings to us of the deep order and beauty that underlies the cosmos. As we drift off to sleep once more, lulled by the timeless lullaby of the moon and the tides, we feel a renewed sense of connection to the natural world and the brilliant minds who have helped us to decipher its secrets. In the silver stillness of the night, we are all astronauts of the mind, exploring the celestial wonders that continue to captivate us, awake and dreaming alike. The tides may be inconstant, but the moon, our eternal companion, remains, a reminder of the enduring mysteries that unite us across the centuries. And so we slip into the waiting arms of slumber, secure in the knowledge that just as the moon will continue to guide the rhythms of the oceans, so too will the restless human spirit continue to seek out the hidden harmonies of the universe, one discovery at a time. As we've seen, the moon's gravitational waltz with Earth is an intricate dance, choreographed by the laws of physics. But the story doesn't end there. In the late 20th century, scientists began to uncover new details about how the moon's influence shapes not just our oceans, but the very life within them. In the 1970s, marine biologists studying the Great Barrier Reef off Australia's coast noticed something peculiar. The corals were synchronizing their spawning, releasing millions of eggs and sperm into the water on just a few nights each year. As they investigated further, they discovered that these mass spawning events always coincided with the full moon. It turns out corals aren't the only marine creatures attuned to the moon's cycle. From tiny plankton to giant whale sharks, numerous ocean species time their feeding, reproduction and migrations to the lunar rhythm. The moonlight penetrating the ocean's surface acts as a celestial cue, a silver beacon guiding the life cycles of the seas. One remarkable example is the Pololo worm of the South Pacific. For most of the year, these worms remain hidden, burrowed into coral reefs. But on just 1 or 2 nights, under the light of a full moon, they emerge en masse. The worms break off their back ends, packed with reproductive cells, which drift to the surface in a pulsing, wriggling swarm. This lunar-triggered spawning frenzy attracts larger fish, which swoop in for a protein-rich feast. It's a vivid illustration of how the moon's influence propagates through the ocean's food web. Humans, too, have long been drawn to the rhythm of the tides. For centuries, coastal communities have planned their fishing, navigation, and even festivities around the ebb and flow of the sea. The Chinese Mid-Autumn Festival, also known as the Moon Festival, is a prime example. Falling on the 15th day of the 8th lunar month, When the moon is at its fullest, the festival is a time for family gatherings, moon gazing, and sharing mooncakes. It's a celebration of the harvest and a recognition of the moon's importance in traditional agriculture and timekeeping. In some places, the moon's pull on the tides has shaped the very landscape. Take the Mont Saint-Michel, a Gothic abbey perched on a rocky islet off the coast of Normandy, France. Surrounded by vast tidal flats, the island is cut off from the mainland during high tide, when the sea surges in at a galloping pace. For pilgrims and monks living on the Mont, the tides dictated the rhythms of life, determining when they could venture out to fish, collect shellfish, or welcome visitors. The abbey's stark beauty and tidal isolation have made it an iconic symbol of the moon's earthly influence. As we move into the 21st century, our understanding of the moon's role in ocean dynamics continues to deepen. Climate scientists are studying how tidal forces might be affecting the melting of polar ice sheets, as the moon's gravitational flex cracks and weakens the ice. Oceanographers are investigating how tides influence the mixing of ocean layers, affecting heat transfer and nutrient distribution. And marine ecologists are uncovering more and more examples of lunar-linked behaviours in ocean species, from the tiniest zooplankton to the largest whales. In a sense, the story of the moon and the tides is still being written, as each new discovery adds another verse to this age-old cosmic ballad. And yet, amidst all the scientific intricacy, there remains a simple, timeless beauty to the moon's dance with the oceans. It's a reminder that even in our fast-paced, technology-driven world, we are still creatures bound to the rhythms of the cosmos. As we drift off to sleep, let's take a moment to appreciate this lunar legacy. The next time you find yourself on a moonlit shore, watching the waves roll in and out, remember, you're witnessing a celestial pas de deux billions of years in the making. It's a dance that has shaped our world, our oceans, and the very pulse of life on Earth. So here's to the moon, our faithful tidal partner. May its silver light continue to guide us, both in our scientific quests and in our moments of quiet reflection. Because in a world of constant change, there's a certain comfort in knowing that the tides will keep rolling, the moon will keep shining, and the ancient dance will go on, as it always has, and always will. And to you, dear viewer, thank you for joining us on this journey through the entwined stories of the moon, the tides, and the countless lives they touch. If you've enjoyed this video, consider giving it a like and subscribing to our channel for more science and history content to lull you into a blissful moonlit slumber. Until next time, sweet dreams and happy moon gazing.